In lesson 3-4, we're going to be looking at the real number system and talking about more of the different types of numbers. In yesterday's lesson, I did refer to the words rational numbers and irrational numbers a little bit. So today we're going to identify and classify real numbers in the real number system, and we're going to be identifying what exactly fits where. As you can see here, some of us probably recognize this as a Venn diagram. So those of us that know how Venn diagrams work, whatever's on the innermost circle, here in the way this is shown, everything in this circle is also in this circle, which is also in this circle. So we need to kind of think that they're all kind of connected there. So when we think about that, a whole number is like the number 3 and 4 and 7 and so on. So when we're talking about whole numbers, we're just talking about the numbers 0 through infinity, and they're all positive numbers. Then we get into integers, and we're talking about -2, and we're talking about -7, and also -9. Okay, but notice that integers still includes whole numbers, so 4, 3, and 7 are also integers along with being called whole numbers. Okay, once we get to rational numbers, we start to talk about, okay, 2/3 and 1/4, and we can say 0.3 repeating because it can be written as a rational number. Again, inside the word rational, we have this word called ratio, and a ratio is a fraction. So if you can write the number as a fraction, then it is a rational number. So one thing I don't like about how this Venn diagram is created is that irrational numbers, it looks like, encompasses everything. However, really what I try to do here is show that irrational numbers are on the outside and they're not in a circle at all. So if anything is out here, it's considered an irrational number. But one thing to remember that a rational number is not an irrational number. So pretty much if anything is in any of these three circles, we can call it a rational number, because the number 4 can be written as 4/1, and therefore it is rational because you can write it as a ratio. So some examples here of irrational numbers would be like the square root of 2. Because 2 is not a perfect square, when you take the square root of 2, you're going to get a number that does not repeat as a decimal, and it never terminates either. So it's kind of like the number pi. Many of us think of 3.14, but really that number goes on and on forever, and it never repeats, and it never terminates. So if you were to start writing the number pi out, you would never be able to finish. It keeps going forever. So we call these numbers irrational numbers, and we try to use different ways to represent them. Like here we came up with a Greek letter of the alphabet, pi, to represent that number. So any square root that is not a perfect square, so if I had the square root of 49, that would actually go all the way in here as a whole number, square root of 49, because the square root of 49 is 7, so it fits right there. So I would need like the square root of 50, which is not a perfect square. Now in here as integers, I would say like the square root of, or the negative square root of 36, because the square root of 36 is 6, and I have a negative. So I could have some square roots in these, but we're thinking about the answers, not what the number actually is. So again, the square root of 49 is 7, and 7 is a whole number, so that's why it fits there. So again, kind of like putting an example in here, we could say the square root of 16 divided by 25, which is going to be 4/5, which is a rational number. So that can fit in there as well. Just trying to give you some examples of what numbers can fit in there. So this kind of just talks about, again, an irrational number is a number that cannot be expressed as A over B, which means cannot be expressed as a ratio or fraction, where a and b are integers, and of course b cannot equal 0 because we can never have b in the denominator. So like the square root of 2 and the square root of the negative square root of 3, they'll keep going forever. That's why it's represented here with the dots. It doesn't actually terminate. Even if your calculator or your screen shows it it's stopping, it does not stop. So we're going to classify some numbers, name all sets of numbers to which 0.090909 ... belongs. So the ... tells us that this number does not terminate. So really we're talking about 0.09, and we're talking about a repeating value. Well, we know that we can represent repeating decimals as fractions because, you know, the whole n equals 0.09 repeating, and then there's two numbers repeating, so we can say 100n equals 9.09 repeating, then we can subtract by n, which is 0.09 repeating, and so on. You guys get the idea. We can make this into a fraction. So this is a rational number, and that would be your answer for this problem. Now, since it can be written as a fraction, you know, we're going to have 99, n equals 9 divided by 99, and so n equals 1 over 11. So again, 1/11 is equal to 0.090909 repeating. Now 1/11, okay, it fits here with rational numbers, but we can't call it an integer and we can't call it a whole number, so it just is out here in this outer circle as a rational number. We know that anything's rational is not included in irrational, so if it's rational, that's it. That's the only thing it can be. Remember, anything on these inner circles you need to also work out. So if it's a whole number, it's also an integer and it's also a rational, and you want to list them all. If it's an integer, it would also be a rational, but not a whole number necessarily. So keep that in mind and make sure you're naming all of which they belong to. So the square root of 25 equals 5, okay, and 5 is a whole number. 5 would fit in here. So 5, this is a whole number, it's an integer, and it's a rational number. So what I would want you to write here is, you know, you can abbreviate. You could say, okay, whole number, it's an integer, int, and it's a rational number. And again, it's okay if you want to abbreviate here with these. So just make sure you include them all. This would be like a 3-point problem. If you didn't have all three, you would lose points. You notice the only thing we're leaving out is irrational number, because if it is a rational number, we wouldn't be able to call it irrational at the same time. So name all sets of numbers to which negative square root of 12 belongs. Well, I know it's a negative, so that means it can't be a whole number. But then the square root of 12, well, 12 is not a perfect square. So I know I'm talking about an irrational number here. And if a number is irrational, then it can't be anything else. It's just irrational. It cannot be an integer. It cannot be a whole number. It cannot be rational. If it's irrational, that's all it is. All right, so example 4 says estimate the square root of 8 and the negative square root of 2 to the nearest tenth with a calculator. Then graph them on another number line. So the square root of 8 with a calculator, we can go ahead and do square root of 8, and that equals 2.828. It says it wants the nearest tenth, so 2.82. We're going to leave it at 2.8 here for this value. So the square root of 8 is about 2.8, and the square root of the negative square root of 2 is going to be 1.41, so we could say 1.4, and we know it's going to be negative because we wanted to say negative square root. So negative 1.4 is about. I should include the fact that this is not equal to, it's about, this is an estimate. And then it says it wants us to graph this on a number line. So I know that I have to go as high as 3 and as low as -2. So I'm going to go here with 0, and then I'm going to go 1, 2, 3, and -1, -2. And then I can graph these points. 2.8 would be about right here. So right here I can say the square root of 8, and -1.4 is almost in the middle, and I'll say then negative square root of 2. So when you actually graph it, don't graph your estimate, graph the original form of the number, just like we have done in the past when we write things out. You want to give your answers the way they were given to you, not with the estimates. We'll just use the estimates to go ahead and graph them. Replace the dot with less than, greater than, or equal signs to make this sentence true. Well, first of all, we know that we're going to have to get these into a common form. Looking at this, the square root of 15 is not a perfect square. I know it's going to be really close to 4 because the square root of 16 is 4. So I'm going to want to figure out how close to 4 is it, because I know this number is also close to 4. So I'm going to want to get these numbers into decimal form. So I'm going to take 3 7/8 and turn it into a decimal. So 7 divided by 8, and that equals 0.875. So I'm going to have 3.875, and then I'm going to want to take the square root of 15, and that's 3.872, and I can round that up to 3.873. Either way, okay, so that's about 3.873. So either way, I know that the 875 is bigger, so this symbol would be greater than. B would be the correct choice, because 3 7/8 is greater than the square root of 15. In example 6, a baseball question, the time in seconds that it takes an object to fall d feet is 0.25 times the square root of d. How many seconds would it take for a baseball that is hit 250 feet straight up in the air to fall from its highest point to the ground? So at its highest point, it's going to be 250 feet. So I'm going to go ahead and plug that number in for d. So I'm going to take 0.25, or 1/4 of the square root of 250. So here it says comparing real numbers to solve a problem. So what we can do here is, if you want, you can kind of estimate 250, the square root of 250 if you want to use a calculator. We're going to say 250, and we'll find the square root of that is going to be almost 16, 15.8. So when we take that number, you can just go ahead and leave it in your calculator. That way we'll have all those numbers, and then we're going to go ahead and multiply by 0.25, and we say, what does that equal? Well, we see it says 3.9528 and so on. So we can go ahead and estimate this maybe to the nearest hundredth. If it's said here, it says actually how many seconds would it take for a baseball. So we could say about 4 seconds, but it does not say anywhere in here that we're supposed to estimate. So we might want to be careful with that and just say, about 3.95 seconds, or we could say about 4.0. So if you're going to the nearest tenth, you are going to want to make sure you include that 0, because we are estimating. So it's all a matter of how we want to write this. We can say it's about 4.0 seconds, and S is usually a good abbreviation for seconds, or otherwise you can put SEC. So about 4.0 seconds, and at least here the 0.0 does tell me that it was 3.9 something, and you round it up. So if you just said about 4 seconds, then I'm not going to quite know that as easily. So If you have any other questions about this, you can check with the online tutor.